All right, here we go. Binary numbers, friend or foe. All right, let's start by just talking about how we look at numbers for the most part now, humans anyway. So I have a number like 432. The numbers are in particular places to indicate how many things that is. That is 432 things. Maybe they're dollars, maybe they're dogs or cats or sheep, doesn't matter. And so it's the placement of the numbers that determines how many of something I have. So this 2 is in the 1 spot, the 3 is in the 10 spot, and the 4 is in the 100 spots. That's why we have 432. So that would be just 30, that would be 2, that would be 400, together 432. All right. Now, that is just one way of numbering. We number in what we call a base 10 system because each of these numbers are based on multiples, or powers rather, of 10. This 2 is in the 1 spot, this 3 is in the 10 spot, this 4 is in the 100 spot. If I kept going, the next number would be in the 1,000 spot, so that's 1. 10 times 1, 10 times 10 is 100, 10 times 100 is 1,000, 10 times 1,000 would be 10,000. I just keep on going in that way. Okay. And for instance, here we have a number 5,807. Okay. That means the 5 is in the, I have 5 thousands, I have 8 hundreds, I have 0 tens, and I have 7 ones. Now, the base that we're working with determines what digits I have available to me to write out a number in that base. Over here, since we're using base 10, we can use all the numbers from 0 to 9. That's what you're perfectly familiar with. 0 to 9, base 10. If you were using base 8, you could use the number 0 to 7, one less than our base. If I was using base 3 numbers, I could use any numbers, any digits from 0 to 2. And of course, base 2 then, I just have two choices, 0 and 1. 0 or 1. Okay? So, here we have, you know what, that's kind of showing through in the back there. I'm going to move that. We'll come back to that. Okay, so here we have base 10. And as I already noted, base 10, the position of the number in the numeral, the digit in the number, is based on what it represents. The rightmost digit is always in the 1 spot, the next digit in the tens, next digit in the hundreds, and then the thousands, so on. If I'm writing base 8, the rightmost digit is always in the 1 spot, the next digit will represent 8, not 10, the next digit will represent 64, not 100, and 512, that's 8 times 8 is 64, times 8 is 512. Base 3, again, the rightmost digit, always 1, then that would be 3, next one would be 3 times 3, which is 9, 3 times 9, which is 27, and so on. And of course, base 2, which is what we're going to talk about, binary, the rightmost digit is always 1, and as we move over, the next digit represents 2, next digit 4, next digit 8, next digit 16, next digit 32. So let's look at a typical number, base 10 number, one of my favorite numbers, the number 11. All right. Now, in base 10, that of course represents 11 things. Okay? Maybe you have 11 crayons in your box because you had a dozen but you lost one. Okay? You have 11 things. You can all picture that, 11 things. We know what 11 means. All right? Now, however, this same number written the same way means something totally different if we're talking about a different base. In base 8, it would represent only 9 things. In base 3, it would represent only 4 things. And in base 2, it represents 3 things. Let's look at why. Again, I'm more interested in base 2, but all these work the same way. The rightmost digit always represents the number of ones we have. So this tells us at all times that we have 1 1. Okay? The next digit represents the number of, well, it depends on the base. If we were talking base 10, it would represent 10. We have 1 10. Where in base 8, it would represent 1 8. Whereas in base 3, it would represent base 3. We represent base 2, or binary, it would represent a 2. So that's why in base 8, this tells us I have 1 8, oh sorry, 1 8 here, and 1 1 for a total of 9. In base 3, I have 1 3 here, and 1 1 for a total of 4. And in base 2, I have 1 2, and a total of 1. Now, always keep in mind that this is just a representation of numbers of things. That's what numbers do. They represent things. So if we're looking at 11 as base 10, this is what I'm talking about. I have one set of 10 and one 1 for a grand total of 11. If I'm in base 8, now that changes somewhat. Now, base 8, I have one set of 8 and one set of 1. So I have 9 things. In base 3, I have one set of 3 and one set of 1 for a total of 4 things. And in base 2, I have one set of 2 and one set of 1, so it's a total of 3. So it's still written the same way, but in base 2, that number only represents 3 items, not the 11 that you're used to thinking of when you see that number. Yes, indeed. Yes, indeed. So let's try something a little more complicated. What if I add another 1 to this? The number 111. Yes, it's called a Nelson. That's a Nelson. Okay. Now, the number 111, I want you to go and think about that for a second. How many items would that represent? You want to pause the tape right now? Think about it. I'll wait a few seconds. Okay, so the number 111 in binary would mean that this 1 represents how many 1s we have. Okay, I have 1, 1. This 1 represents how many 2s I have. So I have 1, 2. This number represents the number of 4s I have. So I have 1, 4. There you go. So the number 111 in binary represents 7 items. Now, binary, you recall, only use the digits 1 and 0. So let's try a number that has a 0 in there. Let's say I made this even larger. I'm going to put a 0 here and a 1 there. So now, how many things does the number in binary 10111 represent? I'll let you think about that for a moment. Okay, so let's take a look. This 1 in this position means I have 1, 1. Okay, this 1 in this position means I have 1, 2. And there you go. This 1 in this position means I have 1, 4. All right. This 0 here means I have 0 8s, so I don't need to account for that. And this here means I have 1 16. I'm going to have to bring in the yellow ones. There's 5. Let's do 4 here. 4. 4. 4. Let's cinch that up just a bit there. Okay. There. So I have 16. That 1 means I have 1 16, 0 8s, 1 4, 1 2, and 1 1. And if you total that up, that equals 23 items in base 10. We'd say that's 23 things. So this is how you would represent 23 things in binary. So it's just a matter of placing either a 1 or a 0 into the slot to that, so that you total up the number you're trying to achieve. Okay? So giving you a number and sorting out what it represents in base 10 from binary. So going from binary, so going from 10111 to 23 is a little bit easier than going the other direction. All right, so let's look at the other direction. Slide these off here. Okay, so here are our placeholders here for binary. And I'm going to write some numbers here, and we're going to have to sort out what the binary representation would be by writing the either 1s or 0s in the appropriate spots here to give us the number that we want. All right. So let's try. Let's try a simple one first here, and I'm gonna give you a chance to work on this. So how would I write? I'm gonna write the decimal number here. How would I write the number? Let's go with 9. How would I write 9 as as a binary number. All right? If you think you already know how, go ahead and write that down right now. Think about it. Okay, excellent. Now, to find out what binary is in what 9 is in binary, I need to look at my choices here and find numbers which, if I added them together, would total to 9. And we have only one choice here. I can take an 8 and a 1. 8 plus 1 is 9. So that means that if I were going to write 9 in binary, I would need 1 8, 0 4s, 0 2s, and 1 1. So 1 0 0 1 equals 9 in decimal. There you go. Did you figure that out? I'll bet you did. So 9 is 1 8, 0 4s, 0 2s, and 1 1. All right? Let's try another one. I'll give you the decimal number. Let's go with, what would be a good one here? Oh, let's do 15. There's a good one. What would 15 be if I wrote it in binary? Give you a second to work on that. All right. Now you can see that if I put a 1 clear out here, I'm already too far. I've got 16, but I only want 15. So I'm going to need a combination of these numbers here. So you're going to have to look at this and see what combination is 8, 4, 2, and 1 is going to total 15. And if you think about it, 8 and 4 is 12, and 2 is 14, and 1 is 15. So that means in order to total 15, I need 1 8, 1 4, 1 2, 1 1 for a total of 15. So in binary, 15 would be written 1 1 1 1. There you go. Splendid. Splendid. Now, let's try something a little tougher here. Let's try, ignore that noise if you can hear that. Let's try 23. All right. So let us pause here a moment. Okay, 23. I need to come up with the combination of these numbers here that are going to equal 23. And let's see. So we need a 16 for sure. Now 16 and 8 is 24, so that's too much. So I know I need 1 16. Okay, 0 8s. So let's see, that'd be 20. Okay, 16 and 4 is 20. So I need a 4. This, put a 1 here, that'll give me another 2, so that's 22. And 1 is 23. So 23 in binary is 1 0 1 1 1. All right, let's do one more. And let's make it a good one. Let's do 57. What would 57 be in binary? Okay, so this one's not easy, but if you think about it, so again, I need a combination of these numbers that will total 57. So 32, clearly, I need at least one of those. Got to get up to 57. So I need to put a 1 there to represent a 32. Now, if 32 and 16 is 48, so I'm still not to 57, so it's good. I can add a 1 there. So now 32 and 16 is 48. How much more do I need to get to 57? Well, I need 9 more. And you already know what 9 is. So that is 1 8, 0 4s, 0 2s, and 1 1. So 57 in binary would be 132, 116, 1 8, and 1 1. So that's 32 and 16 is 48, and 8 is 56, and 1 is 57. So there you have it. So when you're looking at a decimal number, you're trying to figure out what it is in binary, there you go. Now, obviously, this binary method is very cumbersome for us as humans. This is much easier. But this is how computers think. This is not difficult at all for computers, and that's the whole point of this exercise. So we'll discuss more about that in class. All right. Thank you so much.